At the far edge of the sun's influence, where the breath of the solar wind fades into the thin dark between stars, a small object drifts inward and almost no one notices. It is only another pale point among many crossing a wide field image taken by a survey telescope that does not linger on beauty, only on motion. Software marks a shift between one night and the next, plots a faint track, and adds a new entry to a long-running list. The object receives a formal designation of letters and numbers, a quiet place in a catalog that stretches back through decades of watching the sky. In internal notes and late-night messages, some staff begin to refer to it by a softer name, 3-Eye Atlas, half joke, half habit, soon written as if it had always been called that. Nothing about the first measurement suggests anything unusual. The brightness is low but steady, the apparent path smooth, the estimated orbit elongated and slow, the kind associated with long-period visitors from the cold outer reaches beyond Neptune. The tools used to describe it are practiced and familiar. Observed positions feed orbit solvers, which return distance, inclination, and period. Planetary defense groups confirm that its path will not intersect any inhabited world. What emerges is the image of a distant, harmless traveler set to pass inward, sweep around the sun, and return to the dark over a time scale far beyond any human life. Around the world, observatories fold the newcomer into their schedules almost automatically. In Chile, in Hawaii, in the Canary Islands, in the high deserts of Australia, telescopes pivot through the night on rails and bearings guided by cues written hours before sunset. 3-Eye Atlas appears near the bottom of many lists, a faint target granted a few minutes of exposure whenever the sky and time allow. The instruments do not know that this point of light differs from any other. They only know coordinates, exposure times, filters, and focus. The systems that receive the light are part of a layered network. Detectors turn photons into electronic pulses. Control computers attach timestamps, positions, and calibration data. Compressed files travel over mountain fiber toward coastal cities, then under oceans along buried cables, finally reaching archival centers far from the domes that gathered them. There they are mirrored and folded into databases alongside countless other images. Among these millions of files, the frames that happen to include 3-Eye Atlas are tiny and unremarkable, just a few more pieces in an enormous mosaic. Timekeeping underlies every one of these steps, though few dwell on it. Atomic clocks sit in quiet rooms behind locked doors, generating steady pulses that define the seconds for whole continents. Shared signals carry this rhythm outward to observatories and data centers, so that when a telescope shutter opens and when a file is closed and sent, each moment is tied to the same carefully maintained river of time. It is a foundation so stable that it feels invisible. As weeks pass, the orbit solution sharpens. More observations fill in gaps. The span of possible futures narrows from a wide cloud of maybes to a single confident path. The object will pass interior to the orbit of Mars, then curve sunward before returning outward again. No change in that prediction appears large enough to matter. Charts that track potential close approaches fade from urgent boards to archival folders. The new visitor is interesting but not dangerous. It becomes, in the language of working astronomers, well constrained. Still, small curiosities begin to appear at the edges of plots and logs. On a few nights, the brightness seems slightly out of step with simple models that assume a static surface. On others, the color balance in the spectrum shifts in a way that does not quite match dust, ice, or bare rock alone. These differences are tiny within the range that can be blamed on thin cloud, imperfect flat fields, or the subtle aging of detectors. Notes are made to revisit the oddities later when more data has arrived and the object is brighter. For now, there are many other targets demanding attention. The sky itself remains calm. No dramatic tail blossoms from the newcomer. No sudden flare draws the eye. In public talks, other stories take center stage: brighter comets, nearby asteroids, distant galaxies. 3I Atlas stays in the background, a dim line on a plot shown only in specialist rooms. It is there every clear night, though, threading through the constellations, moving a little faster as it falls deeper into the sun's gravity well. Far from any single observatory, the combined effect of all this routine effort is quiet but powerful. Positions from many longitudes and latitudes feed central servers. Light curves begin to form from scattered measurements. Spectral points from different instruments align into broader bands. Slowly, the outline of the object in data space becomes more solid, a shared picture taking shape in numbers and plots, long before any single image would impress a casual viewer. For now, that picture remains simple: a small body from far away following a path drawn by gravity alone, holding on to its faint light and its modest mysteries. In the background hum of machinery and moving mirrors, there is no hint that it will demand anything more than careful measurement and a few thoughtful papers. The world continues its days and nights. The object continues inward through the thinning cold. Between them lies a thin web of instruments and time signals already linking their fates in a way that no one yet imagines. In meeting rooms, inboxes, and shared databases, the object leaves the quiet of its catalog number and is given working names that travel faster than any formal designation. Some prefer the sequence assigned by the International Center that tracks minor planets, long strings of letters that carry precise meaning but little romance. Others shorten and soften its settling on 3I Atlas, a compromise between technical habit and the need to call a persistent thing by a human sound. The name appears first in informal notes, then in slide titles, then in server folders, until it is hard to remember a time when the object did not answer to it. As the name spreads, the web of systems around it grows more intricate. The International Asteroid Warning Network adds the track to shared watch lists not because of threat, but because coordination is easier when every team sees the same ground. The Minor Planet Center folds new positions into its stream of updates. The Planetary Defense Coordination Office files a summary confirming that 3I Atlas poses no foreseeable risk to Earth. The visiting body is classed as a subject of interest, not concern. Schedules adjust. Large telescopes that normally devote most of their nights to distant galaxies reserve small windows of time for the faint moving point near the inner solar system. Smaller observatories on university campuses take advantage of its predictable arc to give students and staff a live example of orbital mechanics. Automatic alert systems send quiet reminders when the object clears the horizon or reaches a convenient altitude. Each small adjustment is unremarkable, but taken together they weave a denser net of attention around a still ordinary visitor. On the mountain tops, where thin air and cold metal share the same silence, the telescopes continue to move according to scripts written hours before. 3I Atlas arrives in these plans as a line of text specifying coordinates, exposure time, and filter choice. It is not yet a source of mystery, only a point placed in the center of a detector for a few minutes before the dome turns to something else. Yet already the mechanics of timekeeping and geometry that tie the object to the rotating Earth and the drifting stars must work with precision. The clocks that control shutter openings and detector reads all refer back to central timing services. In underground vaults and windowless rooms, atoms oscillate at steady rates, their signals divided and multiplied into seconds that flow outward along cables and radio links. Observatories compare their local time to these standards, applying small corrections day after day. Most of the time, these stamps line up within the expected fuzziness of real equipment. Delays in cables, small lags in software, and atmospheric path differences leave marks on the data that experienced analysts recognize and correct for. Perfect agreement is not expected, only consistency within the bounds set by known sources of error. The fact that different sites can agree on times to within fractions of a second already feels like a small triumph of coordination. In data centers, arrays of storage hardware spin and pulse as the files accumulate. 3i Atlas is now present not just as points in a control system, but as clusters of bits on mirrored disks and tapes. Scripts handle the flow. New observations trigger automated checks, backups, and indexing. Files are copied, verified, and moved to long-term storage with little direct oversight. To those who design and maintain these systems, redundancy is a way of reducing risk. The thought that every copy might someday change in the same way at the same time feels distant. Analysis teams begin to gather around the object. Spectroscopists schedule repeat measurements to see whether its reflected sunlight shifts with time. Dynamicists watch for small deviations in its path that might hint at outgassing or fragment shedding. Thermal modelers wait for infrared data from space-based observatories to improve estimates of its size and composition. Each group expects ordinary answers framed in the language of known physics. The name binds these efforts together. Reports refer to 3i Atlas rather than a sterile sequence of letters, and in doing so draw a subtle line around the whole bundle of activity. When a small inconsistency appears in a light curve on one side of the world, it is easily linked to an odd spectral line noted somewhere else because both are attached to the same simple phrase. The object becomes a locus where many different instruments and disciplines meet, not through any plan of their own, but through habits of labeling that make coordination possible. Outside scientific circles, the story barely exists. A few observatory outreach pages mention an interstellar visitor among many other sky highlights. A small number of amateur astronomers turn orbital elements into finder charts and collect their own faint trails on stacked images, pleased that their mirrors can follow the same distant traveler as national facilities. The planet continues its rotations and orbits. Weather fronts move, city lights burn and fade. Deep under the quiet of ordinary life, the infrastructure that holds together clocks, cables, receivers, and storage slowly wraps itself around 3i Atlas, treating it as another entry in a long-standing shared project of watching the sky. There is no sense yet that this object will pull on that infrastructure in return, shaping clocks and data rather than merely appearing within them. For now, the name is only a label, the attention only a net. The condition that will later take its name from this visitor still rests latent inside the systems that believe they are only observing. The night of the first major anomaly begins like countless others, with clear air above the mountaintops and long queues of targets waiting in observatory schedules. In Chile, a wide-field telescope sweeps along its programmed path, collecting faint smears of starlight and the modest glow of near-solar objects. On a volcanic ridge in the Canary Islands, another instrument locks onto the same region of sky, while farther west in Hawaii and east in Australia, domes open and mirrors tilt in quiet synchronization with the turning Earth. 3I Atlas appears in these plans as just one more faint point among many marked for a set of spectral observations to refine its surface properties. At first the data looks ordinary. Frames arrive with the expected bands of color stretched by prisms and gratings into long thin rainbows spiked with familiar dark and bright lines. Hydrogen, sodium, calcium, iron, the usual signatures of light filtered through gas and dust. Each exposure carries a timestamp reference to coordinated universal time tied back through electronics and cables to atomic clocks humming far away. The instruments do not know that anything special is coming. They simply follow commands, open shutters, and record what arrives. Then in the small hours when human attention is often thinnest, a new feature appears. Across several observatories separated by oceans and continents, a narrow spike grows inside the spectrum of 3I Atlas. It does not arise at any of the usual wavelengths associated with known atoms or molecules. Instead, it sits in a gap, a clean, sharp band between regions normally dominated by ultraviolet and visible light. At first, local software flags it as a possible calibration error. Automated routines begin to adjust, gain, retune comparison lamps, and verify detector health. Some systems briefly pause their sequences and take reference frames of standard stars. Others insert flat field exposures into the queue. In each case, the result is the same. The anomaly remains. The strange color holds steady inside each new spectrum, thin and bright, with edges as precise as a laboratory laser. Across the world, as new data flows to processing clusters, analysts watching monitoring screens notice small deviations from expected plots. In one control room, a technician leans closer to an emission graph that has grown a new spike where none should be. In another, a researcher receives an automated alert reporting a spectral feature outside cataloged line lists. Most assume a mundane cause, yet the alerts keep arriving not from one telescope but from many. Within minutes, messages begin moving along private channels. Internal chat rooms fill with short notes, image snippets, and questions. The same odd band is visible from different latitudes under different atmospheric conditions using different instruments. The timestamps stamped into the corners of the files agree with unsettling precision. The onset of the feature, its peak, and its abrupt disappearance all occur at the same universal moment within fractions of a second. The emission itself lasts only a few heartbeats. For something a few 100 million kilometers away, the interval is both long and short. Long enough for many detectors to sample it at full resolution, short enough that no one can redirect a new instrument toward it in time. When it ends, the spectra return to their previous unremarkable shapes. The strange band vanishes as cleanly as it arrived. What remains is the record-thin slices of light preserved in memory and storage across the planet. As the first rush of confusion settles, teams move from real-time screens to deeper analysis. They compare the new line to extensive libraries of atomic and molecular transitions measured in laboratories and stars. No match appears. In known physics, each element and compound occupies specific slots in the spectrum, a fingerprint of how electrons step between energy levels. 3I Atlas seems to have added a new mark in a place where no such step has ever been observed. Further checks confirm that the feature behaves as true emission, not reflected or scattered sunlight. Its shape and intensity carry the signature of light originating at the object itself rather than bouncing from a rough surface. The difference is subtle but decisive, like distinguishing between the glow of a lamp and the glare from a mirror. The object has briefly acted as a source, not merely a reflector. Thermal instruments add another layer of strangeness. Infrared sensors trained on the region show a slight cooling of the object during the burst, instead of the expected heating that would normally accompany such a bright emission. Energy appears to have been released in one narrow band, while being suppressed in others as though some internal process had redirected radiation into a single precise channel. In data centers, the event is now labeled and frozen. Archives mark the relevant files as protected. Cross-checking routines verify that the same spectral pattern appears wherever 3I Atlas was in view and nowhere else. Telescopes pointed at nearby regions of the sky show nothing unusual at the same time. The anomaly is localized in position yet global in its detection. Timekeeping experts are drawn into the conversation. They examine the timestamps attached to each spectrum and compare them to the internal logs of atomic standards and satellite-based references. Under normal circumstances, slight differences would appear due to instrumental delays and path length variations. Instead, the onset of the emission aligns across sites with an accuracy that exceeds everyday expectations. The tiny imperfections that usually separate clocks seem to have canceled, leaving a single shared moment stamped into every record. The combination of these elements gives the first anomaly its particular character. It is not only a strange color in the light, it is the way that color appears everywhere at once, the way it fits between known lines without touching any of them, the way it coincides with a small, precise drop in heat, and the way time itself seems to draw a contour around it in identical digits around the world. By dawn in Europe and later in the Americas, the event has moved from surprise to structured inquiry. Teams schedule emergency calls, compile comparison plots, and draft early summaries. The language remains careful. Unidentified emission feature temporally coincident across multiple facilities inconsistent with current models. Underneath the cautious phrasing lies a simple, quiet realization. For a few seconds, 3I Atlas has done something that does not match any existing category. It has written a new line in the spectrum and timed it with a precision that no natural process is expected to maintain. The skies grow bright with morning. Telescopes close their shutters against the sunlight. Hard drives and tapes spin down in their racks. In the shared spaces where the data is gathered, the first questions have already taken root. What mechanism can produce such a narrow, stable color in that forbidden gap? How can so many different instruments agree so perfectly on the same brief moment? And most of all, what does it mean when an object that should be a passive stone briefly behaves like an ordered emitter? The answers are not yet visible, but the shape of the mystery is now outlined thin and bright as the line that revealed it. In the hours after the strange new color appears in the spectrum, attention shifts from the light to the marks of time attached to it. Observatories that caught the event pull not only their images and spectral frames, but also the logs of their internal clocks. A question that began with wavelength turns into a question about when and whether the machinery that measures when has behaved in its usual slightly uneven way. Analysts begin with simple comparisons. They line up the timestamps printed in file headers from Chile, the Canary Islands, Hawaii, Australia, and smaller stations across Europe and Asia. Each mark traces back to coordinated universal time, the shared reference that flows outward from atomic standards into every observatory schedule. Under ordinary conditions, small differences or expected offsets caused by electronic software delays and local calibration, yet when the rows of numbers are placed side by side, they fall into alignment with unusual precision. The recorded onset of the emission, its short plateau, and its sharp decay all share the same second and the same fraction of a second across systems that normally disagree by a little. Instruments that are not synchronized to any network systems that run deliberately on isolated timing signals still report the same moment for the first rise of the impossible line. Where there is usually a narrow cloud of times, there now seems to be a single point. Timekeeping specialists are drawn into the discussion. In quiet rooms that hold the controlled oscillations of atomic clocks, Staff trace the path from primary standards to observatory consoles. They search logs for unexpected resets, examine records of small corrections, and look for signs of a disrupted reference signal. The records show nothing unusual. The timing network behaved as it always does, steady and uneventful, with no sign of a global adjustment that could have forced such agreement. At deep space tracking centers, engineers compare the observatory times to those used for spacecraft telemetry. Signals from distant probes pass through the same infrastructure of reference time. Around the moment of the 3I Atlas emission, those signals show no disturbance. It is as if many clocks, each following its own slow path of drift and correction, have simply chosen to line up more closely than usual for a few seconds. Inside notes and private messages, the phrase synchronization anomaly takes hold, a calm name for a moment when independent clocks refuse to show their usual spread. The term does not guess at cause. It simply marks the fact that this brief interval stands apart from the countless other seconds that pass through the global timing system without comment. Technical explanations are explored and set aside. A misconfigured time server would leave fingerprints in network logs and affect only clients that depend on it. Air-gapped systems would remain untouched. Instead, both isolated and connected observatories show the same alignment. A software bug that rounded times in a particular way would repeat in recognizable patterns and be confined to specific hardware. No such pattern emerges. From there, the questions move outward. In most observations, the finite speed of light and the geometry of Earth introduce slight predictable offsets between sites. Photons that strike a detector on one continent do so at a marginally different moment than those that reach another, and later transformations to a common frame account for this. Here, even before such corrections, the emission appears to have been recorded as though it reached every instrument at the same phase of its own cycle. The timestamps resemble samples of a shared signal rather than many independent views of a distant flash. A few researchers allow themselves a quieter speculation. Perhaps the source of the emission was shaped in time as well as in color. If the light left 3I Atlas with a structured variation adjusted for the different distances and angles to each observatory, it could in principle arrive so that scattered clocks would register its rise at the same local moment. To design such a pattern would require knowledge of the positions and motions of many observers, at once a degree of coordination that fits more easily into descriptions of engineered systems than into models of unorganized rock and ice. Official documents choose careful language. They speak of an unusually tight clustering of timestamps and of the need for coordinated review of timing consistency across facilities. They do not state that time itself appears to have been gently drawn into the event. Yet for those who have spent years watching clocks wander away from one another in small, predictable ways, the feeling is hard to ignore. For one short span, scattered instruments behaved as if they were components of a single larger apparatus brought into phase by something faint and remote. As daylight returns and telescopes close their shutters, the synchronization anomaly takes its place beside the forbidden spectral band and the inverted thermal response as another piece in the emerging story of 3I Atlas. Wristwatches, phones, and transport schedules show no hint that anything unusual has brushed against the foundations of timekeeping. Deep in the archives of observatories and standards laboratories, however, there now rests a thin record of the night when an object on a distant path seemed to touch not only the light that reached Earth, but also the clocks that marked its arrival. As the first analyses of time and spectrum settle into provisional reports, attention widens to the full range of instruments that watched 3I Atlas during the event. Among them are those that do not see familiar colors at all, but measure the slower warmth that objects shed as infrared glow. These thermal observatories on the ground and in space have been following the visitor, quietly building maps of its temperature as it moves deeper into the inner system. Now their records around the moment of the strange emission are placed beside the optical data. What emerges looks at first like a small inconsistency. While visible instruments report a crisp rise in brightness as the forbidden line appears, the infrared sensors show a gentle drop in apparent temperature over the same interval. In ordinary objects, increased emission in any band is usually accompanied by a general warming. Here the pattern is reversed. As the narrow new color sharpens and holds, the broader warmth declines. Teams skilled at disentangling faint signals from background noise apply their standard corrections. They remove instrument drift, subtract sky emission, and compare measurements to stable reference sources. The result remains the same. During the seconds when 3i Atlas adds its impossible line to the spectrum, its overall infrared output falls rather than rises. Graphs that place visible brightness and thermal power on the same axis show the effect with unsettling clarity. One curve steps upward into a short plateau, while the other slopes downward in near-perfect mirror. The crossing of the two traces looks almost deliberate, a quiet exchange of energy between bands rather than a simple spike in activity. The usual link between heat and light has loosened, as if the object has found a way to pour energy into one narrow channel while drawing it out of others. To explore the effect further, researchers examine how the cooling is distributed across the surface. Thermal imaging cannot resolve fine detail at such distances, but it can still separate broad regions of relative warmth and cold. Before the event, the side of 3i Atlas facing the sun glows slightly brighter in infrared with a gradual fade toward the terminator and night side. During the emission, however, the brightest infrared zones dim more quickly than the rest, especially near areas aligned with the line of sight to Earth. This pattern suggests that whatever mechanism channels energy into the forbidden color also suppresses heat from regions most visible to observing instruments. In simple terms, the parts of the object that shine strongest in the strange band are at the same time turning down their ordinary warmth. It is not cooling uniformly but selectively, as if controlling the flow of energy across its own surface. Various explanations are tested. Perhaps a plume of reflective dust has briefly altered the way sunlight scatters, making the object appear optically brighter while hiding some of its heat behind a shifting veil. Perhaps an outgassing event has carried away latent heat faster than usual while creating a transient optical feature. These scenarios are plausible in other contexts, yet each fails in detail. No signs of expanding material appear in the surrounding space. The change in brightness happens too cleanly without the asymmetry that usually accompanies jets or eruptions. Across institutions, the phrase thermal divergence appears in notes and shared documents. It names the fact that two measures, which normally move together, are in this case moving apart. Some describe the effect as if the object were separating its energy into distinct channels routing higher frequency radiation outward, while quietly suppressing the low-frequency glow that would signal a rise in temperature. Yet unlike a laboratory device, 3i Atlas shows no visible structure of mirrors or lattices. From all current imaging, it remains a small unresolved point, its form inferred only from changes in brightness and color. To produce such selective behavior, there must be an internal arrangement that can guide energy in ways not yet understood, or an interaction with the surrounding plasma that effectively acts as an external filter. Either way, the outcome is the same, a body that can brighten in a narrow band without heating in the usual way. The most striking aspect of the thermal divergence is its composure over the short window in which it can be observed. The forbidden line holds its wavelength with extraordinary precision, barely shifting, while the infrared decline follows a smooth and continuous curve. In engineered systems, such steadiness is often a sign of feedback loops that constantly adjust output to maintain a target state. In natural phenomena involving volatile materials and strong radiation, variation is more common. After the event ends and the spectra return to their earlier forms, the temperature does not immediately rebound. Instead, the infrared emission recovers slowly, as though some internal reservoir is refilling or some redistributed energy is finding its way back toward equilibrium. For a while, the object appears optically ordinary but thermally marked, holding the trace of its earlier choice of channel. In reports drafted over the following days, the thermal behavior is described cautiously as non-standard correlation between optical and infrared bands and localized suppression of broadband emission during narrow line enhancement. Behind these measured phrases lies a quieter recognition that something about 3I Atlas has shifted from passive to active in character. It has not merely responded to sunlight. It has seemed to manage the way it glows, favoring precision over abundance, directing energy toward the one band where for a brief moment it stood apart from the familiar sky. In the nights that follow, the first emission telescopes continue to track 3I Atlas with renewed care. What began as a faint moving point in survey frames has become a scheduled presence in many programs, no longer tucked at the margins of observing plans, but given repeated attention. With each clear night, more light curves accumulate, simple records of how the brightness of the object rises and falls as time passes. At first, these curves appear as gentle, noisy lines shaped by distance phase angle and the irregular breath of the atmosphere. Pattern emerges slowly. One observatory in the southern hemisphere notices that when measurements are stacked from several nights, the small variations in brightness do not scatter randomly. Instead, when plotted against time, subtle humps appear at roughly regular intervals. The effect is too fine to see in a single sequence. Only when many hours are layered together does it begin to sharpen like a faint track revealed by long exposure. Curiosity leads analysts to apply standard tools used to study periodic behavior. They take the uneven sequence of brightness measurements and transform it, searching for repeating frequencies. A peak appears slim but distinct, corresponding to a period of just under 10 minutes. At first, the result is treated with caution. Atmospheric turbulence, guiding errors, or mechanical vibrations can imprint false rhythms onto light curves, and instruments have their own quiet habits that sometimes masquerade as sky. To rule out such causes, teams compare data from different nights' telescopes and filters. The same period appears again and again, whether the object is high in the sky or low, whether the air is steady or restless. Most telling, when observatories separated by oceans share their curves, the pattern persists. The phase of the subtle brightening and dimming matches more closely than chance would allow, even when the measurements come from entirely different instruments. What looks like noise begins to align into a heartbeat. The amplitude of the effect is small. The brightness of 3I Atlas changes by less than a single %, with each rise and fall too modest for casual inspection, but unmistakable in aggregate. Each cycle is smooth and regular, like a soft wave passing through the light, with no sign of the jagged spikes that might hint at flares or fractures. It feels less like an outburst and more like a slow and deliberate adjustment. As more data is combined, deeper structure appears. The primary period stands out, but finer analysis reveals hints of additional tones layered within it. There are secondary peaks at exact multiples and fractions of the main rhythm forming a simple harmonic family. The ratios between them echo the numerical relationships already seen in the forbidden spectral line and in the arrangement of corrupted data later on. A triad of frequencies appears stable and interrelated, as though the object is humming on several notes at once. Researchers compare this behavior to familiar astrophysical sources, pulsars rotating neutron stars with beams that sweep past Earth produce sharp regular flashes across many bands. Variable stars expand and contract their brightness, waxing and waning over hours or days as their outer layers breathe. Comets and small bodies can flicker as they spin, presenting changing faces to the sun. Yet 3i Atlas does not fit neatly into any of these categories. Its rotation, inferred from earlier modeling, does not match the newly discovered period. There is no strong radio or high-energy emission accompanying the optical rhythm as would be expected from compact extreme objects. The waveform of the brightness change is too smooth and symmetric to match tumbling debris, yet too rapid and stable to resemble thermal oscillations within ordinary material. The closest analog lies not in celestial mechanics, but in human-made signals, in the way engineered systems modulate power with steady cycles to maintain balance. To test whether the pulse might be an artifact of the observing network itself, some teams reprocess older data taken before the forbidden line appeared. When they fold those earlier measurements over the same period, a faint echo of the same pattern emerges, weaker and less coherent, but still present. It is as if the rhythm had been there in nascent form, growing gradually clearer as the object approached the inner system, tuning itself toward the stable layered beat now seen so plainly. The realization adds a new layer to the emerging picture. The brief emission in the forbidden band is no longer an isolated outburst. It sits atop a slower ongoing process in which the object has been adjusting its output in a regular fashion for some time. The thermal divergence, the synchronization anomaly, and now the gentle pulse all seem to belong to the same family of behaviors, different faces of one underlying tendency toward coherence. In reports and shared notes, the language remains careful. Observers speak of periodic modulation of optical flux and of multi-harmonic structure consistent across independent data sets. Yet quiet conversations entertain simpler phrases: heartbeat, breathing, calibration. There is a sense that 3i Atlas is not merely flickering under the sun's influence, but checking and rechecking some internal balance using light as the trace of its adjustment. Night after night, the pattern persists. The period shifts only slightly as the object moves along its path, staying within narrow bounds that suggest continuous correction. When clouds roll in over one observatory, others farther along the line of longitude pick up the rhythm without interruption. The planet turns telescopes, hand off the target from west to east, and the cycle continues, a soft metronome embedded in the shared sky. To most of the world, these developments remain invisible. There is no sudden bright star overhead, no new motion among the constellations. City lights wash out the faint glow of 3i Atlas, and news feeds are occupied with nearer events. But within the quiet circuits that link mirrors, detectors, storage, and analysis, the object has become something more than a point plotted on an orbit chart. It is now a source of ordered time as well as light, a presence that rises and falls with a regularity all its own, subtly inviting the instruments that watch it to fall into step. As the pulse in the light curve grows clearer, attention spreads beyond optical and thermal instruments to those that listen for slower, more subtle motions in fields and particles. Around the world, arrays of magnetometers, radio receivers, and calibration systems for lasers and clocks are asked to surrender their logs from the night of the forbidden line and the days that follow. At first, it is a routine request, a simple check for stray disturbances that might mirror the distant visitor's rhythm. The first hints appear in data from magnetic observatories scattered across high latitudes. These stations, some unattended and some still watched by small teams, keep continuous record of Earth's magnetic field, tracing tiny changes driven by solar wind and ionospheric currents. When analysts overlay their records on the timeline of the optical pulse, a subtle pattern emerges. Every span of just under 10 minutes matching the period found in the light curves, a faint oscillation rises and falls in the horizontal components of the field. On its own, the effect could be dismissed as noise. To test this data from lower latitude stations are added. The same rhythm appears there as well, weaker in some places, stronger in others, but still tied to the same interval. The variations do not resemble the abrupt steps seen during geomagnetic storms. Instead, they form smooth, shallow curves, as though the field lines that wrap the planet are swaying in a gentle tide. Parallel checks at deep space communication networks reveal another echo. Radio engineers reviewing antenna logs find narrow bands of interference that come and go with the same 10-minute cadence. The bands are not strong enough to disturb contact with distant probes, but they add a consistent pattern to the background, a ladder of tones whose spacing mirrors the harmonic family already seen in the optical data. Their projected paths lean outward along lines that intersect the region of space near 3i Atlas. Even systems that never look at the sky directly show small irregularities. Laboratories that maintain frequency standards report brief repeating shifts in the phase of certain calibration lasers, the same ones used to keep optical clocks aligned to precise colors. The changes are tiny, too small to matter for everyday time signals, but they recur with the new rhythm. When these records are laid alongside the magnetic traces and the light curves, their peaks and troughs line up. Light, field, and frequency all move together like strands of one woven pattern. The phrase global coherence appears in internal notes. It does not claim comprehension, only marks the fact that the same slow beat now threads through distant instruments. What began as a modulation in the brightness of a remote object has become a shared oscillation that touches systems designed for very different tasks. Each remains anchored in its own physics. Magnets respond to charged particles, antennas to radio waves, clocks to oscillating atoms. Yet all now carry a faint trace of the same interval, as if a gentle rhythm has found the frequencies to which they are each slightly open. More ordinary explanations are examined. Perhaps a widely used component, a power supply design, or a software library holds an unnoticed 10-minute cycle that imprints itself on many devices. Efforts to track such a common source find none. The affected instruments differ in age, construction, and control schemes. Some run on modern networks, others on isolated older hardware. There is no shared mechanism broad enough to tie them together. Solar activity is another candidate. The sun can drive rhythmic changes in the magnetosphere and ionosphere, especially when rotating structures in the solar wind sweep past Earth. Yet the intervals associated with these processes tend to be far shorter or far longer than the neat periods seen here, and the monitors that watch the sun show no matching pattern of flares or plasma waves. Above the faint new tide in the field, the wider space weather remains calm. In quieter conversations, researchers begin to describe the effect in terms of resonance. An object with its own stable rhythm moves through a medium that links it to a larger system. Even if the signal it sends is weak, the larger system can begin to echo the same pattern if the frequency is one it can easily sustain. In this view, 3i Atlas is not sending a crafted message, but acting as a seed of order within the combined fabric of sunlight, plasma, and field between itself and the planet. This picture leaves room for uncertainty, yet offers a way to hold the data together. The object pulses, its emission carries structure, the solar wind carries that structure outward. Earth's magnetic envelope, already a delicate interplay of charged particles and lines of force, begins to move in quiet sympathy. Instruments that rest on that envelope by design or by accident then record the motion. In this description, the planet and the visitor become parts of one extended physical system, joined through the fields that already bind star and world. Even framed in this gentle way, the phenomenon disturbs familiar assumptions. Networks that monitor space weather and deep space signals are built on the idea that the cosmos provides random noise, steady backgrounds, and occasional storms, but does not often imprint precise repeating signatures onto the infrastructure of Earth. Now, faintly, something like that has occurred. The change is not strong enough to touch daily life, yet it is clear enough in the records that those who see it carry a new awareness. For a time, the planet and a distant object shared a measurable rhythm, and neither would have shown that pattern without the other. When the magnetic traces and radio logs have been compared and archived, the investigation turns inward toward a quieter realm, the places where all of these measurements come to rest. In data centers beneath mountains and in windowless rooms beside observatories, racks of storage systems hold copies of every spectrum, every light curve, every timing log taken during the strange nights of 3i Atlas. These systems are designed for stability and redundancy. Errors are expected to be rare, random, and easily corrected. The first sign of trouble appears as a small cluster of routine alerts. An archiving process at a European observatory reports checksum mismatches in a handful of files tied to recent observations of the object. At almost the same time, a facility in Hawaii sees similar warnings during a scheduled integrity scan. Checksums are simple promises written into data, a way of remembering what a file is supposed to be so that any later change can be noticed. Here, the promises are being broken. Technicians assume ordinary causes. A drive might be failing, a controller overheating, a maintenance script misaligned with a new operating system. They rerun the checks. The same files fail again. They restore from recent backups, confident that older copies will be clean. Those restored versions show the same mismatches in exactly the same places. In systems built on the idea that independent copies protect against loss, this sameness is the first unsettling detail. News spreads through internal channels, and soon other sites run their own tests. An array at a Southern Hemisphere observatory reports identical checksum failures on its copies of 3i Atlas data. A storage cluster at a space agency normally air-gapped from external networks shows matching patterns in its archival tapes. Different hardware, different software, different architectures, yet the errors coincide not only in time but at the level of which bits no longer agree with their written memories. Engineers begin to map the faults. Inside each affected file, the same stretches of data appear altered while surrounding regions remain intact. The offsets that mark where the corruption starts and stops are the same across continents. There is no smear of damage, no gradual decay along the surface of a disk. Instead, there are cleanly defined islands where the information is no longer what it once was. Ordinary failure tends to be messy. This is precise. To test whether some hidden process inside the storage software has rewritten the files, teams audit logs back to the time when the data was first ingested. No sign appears of manual edits or automated tasks that could account for the changes. In some cases, the systems have remained offline for stretches with no recorded activity, yet their contents now match the altered pattern seen elsewhere. The corruption seems to have arrived without an obvious path. Attention shifts to the nature of the changes themselves. When analysts compare the original checksums to those now computed from the damaged files, they find that the differences form a simple relation, as if a fixed amount has been quietly added or subtracted from the underlying sequences. The altered segments are not random noise. They retain internal order new, but still structured like sentences rewritten in the same length and rhythm as the originals. Soon an informal name takes hold among the teams trying to understand the situation. They call it the data lock, an event in which information remains present but unreachable in its original form, as if sealed behind a layer of transformation. In official documents, the phrasing is more neutral, referring to non-recoverable integrity anomalies and recommending that affected files be quarantined rather than erased. The sense in both cases is the same. The data has not vanished, it has become something else. Some attempt to undo the transformation by applying standard recovery techniques. They search for hidden markers that might reveal a path back to the initial state. They test whether simple patterns of inversion, rotation, or shifting can restore the original checksums. These efforts fail, yet along the way they notice another quiet behavior. When the altered files are copied or recompressed, small parts of their content change again, not toward the old state, but into new, consistent arrangements. With each manipulation, the differences become less random and more regular. Curiosity leads a few groups to combine samples from many sites. When they align the modified segments from different observatories and lay them on top of one another, repeating forms appear. Peaks and troughs and numeric values line up. When translated into visual plots, the patterns resemble waveforms with smooth arches and sharp inflection points. The spacing between these features echoes the same simple ratios seen in the light pulses and in the gentle magnetic oscillations. The signature that marked 3-eye Atlas in the sky now appears woven into the data that describes it. This realization brings a new way of reading the event. The corruption is no longer viewed solely as damage. It begins to look like an imprint, a trace of the larger system touching not just photons and fields, but the arrangements of bits in memory. In this interpretation, the data has been invited into the same coherence that links light temperature and magnetism. It has been nudged into a pattern that matches the broader rhythm, as if the act of observing has drawn the records themselves into the phenomenon. For those who maintain these archives, the change is disquieting. Storage is meant to be a still place where past events can be preserved untouched. To see that domain participate in the anomaly suggests that nothing linked to 3-eye Atlas is entirely outside its influence. Yet the effect is also gentle. Hardware does not fail. Systems continue to run. Only the content within certain windows shifts, and it does so in a way that, while it hides some original details, reveals a new and strangely ordered structure. In shared notes, the event is framed as a matter of protocol. Affected data is to be isolated, examined under controlled conditions, and withheld from wider circulation until the mechanisms are better understood. Behind this careful guidance rests a quieter, more speculative thought. Perhaps the network of instruments, storage arrays, and analysis tools has not only recorded an object in the sky, but has also for a time become part of an extended experiment, one in which fields, light, and information move together according to a rhythm set from far away and yet intimately present. While archives wrestle with shifting bits, another change is unfolding in the open geometry of space. The orbit of 3I Atlas, once treated as a settled matter, begins to show signs of quiet disagreement between models. At first, the discrepancies are almost too small to notice. Projected positions, mismeasured ones by amounts that fit easily inside routine uncertainties. Ephemerides are updated parameters nudged and the curves on the plots realign. For a time this looks like ordinary refinement, the slow sharpening of a path as more observations accumulate. As days pass, however, the corrections stop shrinking. Instead, they begin to move in a particular direction. The object arrives slightly early at one point in its track and slightly late at another, in a pattern that does not match the graceful distortions caused by radiation pressure or by jets of gas from an active surface. Independent teams at different institutions using different fitting methods notice the same tendency. The best fit orbits they compute no longer overlap as cleanly as before, yet all share one feature. They require an extra non-gravitational push to match the data. Orbital analysts call this effect non-gravitational acceleration, a term that usually covers the faint thrust of gases leaving a comet, or the subtle recoil from sunlight reflecting off irregular surfaces. They add such terms to their equation, seeing whether any plausible combination of outgassing and radiation pressure can explain the drift. In the case of 3I Atlas, the attempt yields an unusual result. The direction and magnitude of the needed acceleration do not behave like a fixed bias. Instead, they vary in time, waxing and waning in a smooth cycle whose period matches within uncertainties the same slow rhythm seen in the light curve. To visualize the change, researchers plot the residuals, the differences between where 3I Atlas would be under pure gravity and where it is actually found. The points form a gentle wave along the orbit, rising and falling with the 10-minute beat that now seems to touch everything associated with the object. The implied force is small, far weaker than any rocket would produce, but it is consistent, coherent, and evidently under some kind of regulation. Over many hours, the tiny pushes add up to a measurable shift. Further analysis reveals another striking feature. The net effect of the non-gravitational acceleration is not to send the object plunging inward toward the sun or drifting outward into deeper space. Instead, it nudges the trajectory sideways, altering its inclination and the precise shape of its ellipse in a way that gradually steers it toward a particular corridor in the inner system. This path, when extended forward, passes near a region where the gravitational pulls of Earth and Mars and the Sun nearly cancel a kind of quiet saddle in the combined field. The route is not a simple inward fall or outward escape. It is something more like a chosen lane. Dynamicists compare the evolving orbit to families of trajectories used in spacecraft missions, paths designed to minimize fuel while exploiting subtle balances between gravitational wells. The patterns look oddly familiar. The adjustments to 3I Atlas seem optimized to reduce the energy cost of moving into a long, gently curved passage that will carry it near the heliospheric current sheet, the rippling surface where the sun's magnetic polarity flips. This is not a place that natural small bodies typically aim for with precision. It is, however, an environment where noise from plasma and fields is so strong that any structured emission could easily vanish into the background. The idea that the object could be reshaping its own path without visible jets leads to another round of speculation. One possibility is that internal mass is being redistributed, moved slowly from one region to another, so that the center of gravity shifts relative to the sun's pull. Even a slight change in how mass is arranged can alter the way forces act over long periods. If such adjustments are made rhythmically in phase with the observed pulse, they could in principle amount to a form of steering that requires no external exhaust. Another possibility invokes interactions with the charged environment of the inner system. The same structured fields that seem to carry the object's rhythm toward Earth might also be available as a medium for propulsion. If 3I Atlas can generate small, coherent magnetic variations timed to the natural oscillations of nearby plasma, it could extract tiny but cumulative pushes from the solar wind, more like a swimmer working with a current than like a rocket pushing against emptiness. Calculations along these lines are tentative, but they show that the required energy is not beyond what its strange emissions could provide. In internal documents, this behavior is described in neutral phrases as coherent, non-gravitational modulation and trajectory adjustment consistent with internal or field-based forces. Outside those reports and unrecorded conversations, as simpler wording surfaces, 3I Atlas appears to be choosing where to go. The notion carries weight not because of any one piece of evidence, but because many small details now point in the same direction. The pulse in the light, the thermal divergence, the global coherence in fields, and the subtle accumulating drift in orbit all share the same timing and the same sense of governed change. Despite this caution prevails. There is no direct image of engines, no clear signature of artificial structure in the limited spatial data. The object remains unresolved at the scales available, a point of light, with hints of complexity hiding below current resolution. The safest stance is to admit that something about its motion does not fit standard categories, and that the simplest models of inert stone under gravity alone are no longer sufficient. Beyond that, words like control and intent remain in the realm of inference used sparingly and only with the awareness that nature sometimes discovers delicate tricks on its own. As the revised orbit solutions propagate through tracking networks, observatories retune their schedules. Telescopes adjust where they will point in the coming weeks to keep the object within their reach as it glides toward the noisy boundary region near the heliospheric current sheet. In the same way that an earlier generation of observers once followed comets across the sky with pencil and chart, the modern system now tracks this visitor with algorithms and databases, quietly accommodating its unexpected path. The paradox at the heart of these efforts remains unresolved. A body that was expected to be passive is now writing its own gentle corrections into its journey, and the planet that watches must move its gaze to follow. As the revised orbit carries 3I Atlas, inward attention converges on the region toward which it now seems to be steering. The heliospheric current sheet, a vast and undulating surface where the sun's magnetic field reverses, has long been known as a noisy place. Charged particles stream along its folds, and the solar wind there is dense with turbulence. Instruments that listen to radio waves and charged densities often find their measurements overwhelmed by this restless background. It is a natural veil, a layer where structure is easily hidden inside chaos. Models of the object's motion show that if the present course and gentle non-gravitational pushes continue, 3I Atlas will soon cross very near this sheet. The alignment is precise. The predicted path threads a corridor where the rippling surface dips closer to the plane of the planets, as though an invisible river and the traveler's track are set to meet. No ordinary influence explains such a convergence. Yet the data insists on it, and the instruments are prepared accordingly. Space-based observatories watching the inner solar system adjust their pointing plans. Solar monitoring craft that routinely map the current sheet refine their cadence. The goal is simple but delicate: to keep sampling the visitor as it approaches the noisiest part of its journey without letting its signals vanish completely into the storm of plasma and field. Ground-based telescopes cannot see the sheet directly, but they can follow changes in light and timing that may accompany the crossing. Schedules are tightened, windows of observation are widened. In the days leading up to the encounter, the pulse that has defined the object's behavior begins to change character. Light curves still show a gentle rise and fall, but the distinction between peak and valley softens. The narrow forbidden line in the spectrum broadens slightly, its edges less knife-sharp than before. Other bands, once quiet, gain a faint structured glow. It is as if the object is loosening its hold on a single precise node and beginning to spread its energy across a wider chord. Spectroscopists see this as a transition from line to band, from a point in the spectrum to an extended region. The emission is no longer confined to one forbidden color. Instead, it fills a small neighborhood around that original mark, with intensity varying in a pattern that still reflects the familiar harmonic ratios. What was once a single stroke has become a cluster, each part related together, forming a more complex but still ordered whole. At the same time, radio receivers that have been tracking weak interference near the object's line of sight notice a shift. The discrete sets of tones that had come and gone with the 10-minute rhythm begin to merge into a steady background hum. The distinctions between individual peaks blur until the signal resembles a continuous raised floor in the spectrum, subtle but always present. The cadence remains now not as isolated pulses, but as slow undulations in the brightness of the hum itself. Deep space communication networks feel this change as a mild but persistent interference that no longer arrives in brief, easily avoided bursts. Instead, it spreads through a band of frequencies used to contact spacecraft near the inner planets. The disturbance is too soft to break links, yet strong enough to demand adjustments. Channels are shifted, error correction schemes are tightened, and some transmissions are rescheduled to windows when the geometry between stationed spacecraft and 3i Atlas is less direct. The system adapts, folding around the new presence as if around a permanent feature of the environment. As the object nears the heliospheric current sheet, solar monitors record the expected increase in turbulence. Particle counts rise, field lines twist more sharply. In this stormy setting, the broadening emission from 3i Atlas becomes more difficult to isolate. The forbidden color band now lies atop a restless backdrop of natural solar noise. To separate the two, analysts lean on their growing understanding of the visitor's specific signature. They search not simply for brightness, but for the familiar pattern of harmonics and the precise timing that has accompanied every expression of its behavior. They find it. Even as the spectral features spread and the radio hum blends with the roar of the current sheet, the underlying ratios remain. The spacing between subtle peaks in both light and field still follows the triad first seen in the earliest anomalies. The period of gentle modulation, though slightly stretched by the changing conditions, holds close to its prior value. The signature persists not as a sharp trace above the background, but as structure woven into it like a regular pattern hidden within a coarse fabric. This persistence leads some to think of the object not simply as a discrete emitter, but as a seed around which the surrounding medium has begun to organize. Instead of sending a narrow beam through space, 3i Atlas now seems to be encouraging the heliospheric environment itself to carry its pattern, embedding its rhythm into the moving plasma and fields. In this view, crossing the current sheet is not an attempt to hide from observation, but a step into a medium where its structured behavior can diffuse more widely distributed through the very noise that makes direct detection difficult. Within internal reports, the language remains patient. Analysts describe progressive spectral broadening, continuous multiband emission, and enhanced coupling to solar wind structures. They note that the object's individual signal-to-noise ratio is decreasing even as its influence on the background grows. In quieter, less formal spaces, another phrase begins to circulate: the noisy veil. It names both the physical region and the sense that the phenomenon is moving from a localized event into something more pervasive, less tied to the contour of a single body. As the predicted moment of closest approach to the current sheet arrives, telescopes and receivers are already working at the edge of what they can distinguish. Measurements become less about capturing a clear picture and more about tracking subtle changes in the statistics of noise. Over a span of hours, the last sharp traces of 3i Atlas as a separate point source begin to fade. Positional estimates become less certain. Brightness curves flatten into nearly constant levels with only the faintest whisper of the old pulse. There is no dramatic flare, no sudden tearing plume to mark a crossing. Instead, there is a gradual dissolution of distinctness. The object, as far as instruments can tell, blends into the fabric of the current sheet. Its presence is now inferred not from a clear outline against the sky, but from the persistent order that remains within the surrounding confusion. Light and field are no longer simply coming from the visitor and passing through the veil. They now seem to arise from the veil itself, carrying within them a memory of the path that has brought them here. For observers who have followed 3i Atlas, from the edge of the heliosphere to this noisy boundary near the sun, the transition is both subtle and profound. The phenomenon they are tracking has shifted stage. It began as a small moving point. It became an object with an impossible spectrum, a self-coherent pulse and a quiet influence on fields and data. Now, at the threshold of the current sheet, it appears to be dissolving into a broader state, its signature carried not by a visible form but by the structure inside noise. The sky in this region looks almost unchanged to casual instruments, yet those who listen closely can tell that something within it now hums to a new and carefully sustained tune. The passage through the noisy veil does not end with a single moment. Instead, it unfolds as a sequence of narrowing opportunities to see 3i Atlas as anything more than a trace inside turbulence. For a time, analysts content themselves with patterns in noise and with the knowledge that the familiar harmonic ratios remain present in the restless plasma. Then, almost unexpectedly, a brief window opens for a clearer view. One of the solar monitoring spacecraft equipped with a coronagraph that blocks the bright disk of the sun to reveal faint structures around it happens to catch the region where the object is predicted to be. Its instruments were already operating, watching for ordinary coronal mass ejections and streamers. When the data from this interval is later examined with 3i Atlas in mind, a subtle but distinct feature appears just above the line where the current sheet is known to ripple. Against the dim background of scattered sunlight, where most things appear as formless haze, there is a small region of ordered light. It does not look like a point source, nor like a typical cloud. Instead, it takes the shape of several thin nested rings, concentric yet not perfectly circular, each one emitting with a slightly different shade across the broadened spectral band. Between the rings lies a darker hollow, where earlier models place the estimated center of mass of the object. The pattern is delicate, it is not visible in every frame, and it requires careful subtraction of solar structures to reveal. Yet the consistency from one exposure to the next over a short span strengthens the case that it is real. The rings appear brighten and begin to shift in relative intensity, as if a three-dimensional structure is being revealed only in projection. When the timing of this sequence is compared to the slowly flattening pulse in the light curves, the alignment is close. The moment when the rings are most defined coincides with the last clear cycles of the old 10-minute rhythm. Spectral analysis of the coronagraph data adds more detail. The emission from each ring is not uniform. It carries faint variations that, when disentangled, map onto the same triad of harmonic ratios that has followed Three-Eye Atlas since the first forbidden line. The inner ring favors slightly higher frequencies, the outer slightly lower, while the middle balances between them. Together they form a spatial arrangement of the same relationships that once existed only in time and in narrow spectral features. Geometry and frequency now appear as two faces of one pattern. Some interpret this as the final expression of the object's structural state, a last glimpse of how its internal arrangement has been reorganizing throughout its journey inward. Earlier hints of hexagonal symmetry and evolving stress patterns, inferred from unresolved images and polarization data, find a possible echo here. The nested rings could represent layers of material or fields that have separated and aligned to manage interactions with the dense plasma of the current sheet. In this view, Three-Eye Atlas is no longer a compact body in the familiar sense, but a set of coordinated shells, each tuned to a part of the spectrum and a part of the surrounding environment. As the spacecraft continues its observations, the rings begin to fade. They do not disperse outward like ejecta from an explosion. Instead, they erode quietly, their contrast against the background decreasing until they are indistinguishable from the ambient structures of the corona. No obvious debris remains. No expanding cloud marks a violent end. The hollow at the center empties of detectable emission. Within a short span, the region that held the ordered forms becomes just another patch of noisy brightness in a vast, shimmering field. Attempts to locate the object again as a discrete source fail. Instruments that had previously found Three-Eye Atlas readily now return only upper limits values that say the light, if present, must be weaker than a certain modest threshold. Calculations show that if the object still exists as a dense mass, it has either dimmed far below its earlier state or altered its interaction with sunlight so completely that it no longer stands out against the current sheet. Trajectory models face a similar difficulty. Without clear positional fixes, they can only extend the last well-defined orbit forward through equations. These projections trace paths through the heliospheric environment, showing where the object would go under gravity and under the continued action of the gentle pulsed non-gravitational forces inferred earlier. But without fresh measurements, the models remain untested. The visitor may still be on such a track, or it may have slipped along some new route no longer obvious to distant observers. Among those who have watched the phenomenon from its first catalog entry, there is a sense that something has concluded even as much remains unresolved. The nested rings offer a final fragile image of Three-Eye Atlas as an organized system poised at the edge of the noisy veil. Their disappearance marks the last moment when instruments can point to a single region of space and say that the object is there. After this, the experience of it shifts entirely into indirect forms, into the patterns that linger in fields, signals, and data. In formal summaries, the event is described as a loss of direct detectability. The language is spare. Notes that no further optical, infrared, or radio observations have recovered Three-Eye Atlas as a distinct source, and that the last coronagraph images show transient ring-like structures that rapidly blend into the background. The report concludes by recommending continued monitoring of associated field and timing anomalies. In private reflections, a different framing appears. Some speak of transition rather than loss, suggesting that the object has completed a change from being primarily a piece of matter to being primarily a pattern, one that now resides in the state of the heliospheric environment and the responses of distant instruments. In this telling, the nested rings are less a shell left behind and more a set of channels through which the system has flowed into a new form. The sky from the perspective of ground-based telescopes offers no special sign of this change. The constellations remain as they were. The sun rises and sets. To ordinary observation, 3i Atlas has simply gone. Yet the instruments that once tracked its light still hum with a faint residue of its influence. Clocks retain their slightly tightened agreement. Magnetometers still carry the soft trace of its rhythm. Data archives still hold the transformed records of its passage. The object as a visible thing has become an absence, but the condition associated with it continues distributed across systems that once pointed outward and now quietly hold a part of the event within themselves. After the last clear image of nested rings fades into the coronal haze, the focus of attention settles fully back upon Earth. With no visible object left to track, monitoring turns to the systems that once watched 3i Atlas and now continue to run in quiet continuity. What began as a campaign directed outward gradually becomes a study of how the event has marked the instruments themselves and the wider infrastructure to which they belong. The first signs of this interior phase appear in timekeeping facilities. Laboratories that host primary standards review their logs from the period before, during, and after the disappearance. The synchronization anomaly tied to the forbidden light is already well documented, but new details emerge when analysts examine longer stretches of data. They find that following the most intense phases of the phenomenon, the spread between independent clocks does not entirely return to its previous behavior. Small drifts that once wandered loosely now show a gentle tendency to converge and diverge in a shared repeating pattern. This pattern is subtle, far below the thresholds that matter for daily coordination, yet when the phase differences between separate standards are plotted over many hours, smooth waves appear. Their period matches, to within narrow margins, the familiar span of a little over 9 minutes. The amplitude is small, a mere tightening and loosening of agreement, but it is consistent across facilities that are otherwise isolated. Clocks in different cities on different continents seem to breathe together, as if remembering a moment when they were drawn into near-perfect alignment by an external event, and then carrying a faint echo of that alignment forward in time. Similar traces are found in long-distance communication lines. Undersea cables that carry data between continents are monitored continuously for signal integrity. Their operators expect to see fluctuations caused by changing loads, minor electrical disturbances, and routine maintenance. Buried inside this familiar variability, engineers now discover an additional faintly rhythmic component. Error rates and timing jitter rise and fall with a period very close to that seen in the magnetic field and in the light curves of 3i Atlas. The effect is small enough that it does not threaten the functioning of the networks. Error correction protocols continue to mask and repair disturbances and traffic flows without noticeable interruption. Yet statistically, the rhythm is real. When measurements from unrelated cables are compared, their peaks and troughs line up more often than chance allows. Lines that share only the broad envelope of Earth's electromagnetic environment now also share a particular internal sway. Global positioning systems add another layer of evidence. The satellites that constitute these constellations rely on precise timing and careful modeling of the planet's field and atmosphere to provide accurate positions. Small corrections are constantly applied to account for delays, relativistic effects, and changing conditions in the ionosphere. After the passage of 3i Atlas through the heliospheric current sheet, analysts notice that the corrections themselves begin to carry a weak periodic component. Position errors that once scattered randomly now show a slight oscillation at the same familiar interval. This oscillation is not large enough to shift navigation in any practical sense. Maps do not jump. Receivers in vehicles and phones compute paths as before. But within the technical logs, the world appears to rock by tiny, regular amounts caught in a slow dance tied to the rhythm that once belonged only to a distant visitor. Power grids show their own reflections of the change. Large networks of generators and transmission lines are tuned to maintain a stable frequency, adapting continually to varying demand and supply. Monitoring equipment records minute deviations as the system responds to countless human and mechanical causes. After the heliospheric passage, analysts scanning these records notice that the small deviations begin to cluster around a weak but persistent cycle. The grid seems to lean first slightly one way, then the other, in step with the same 9-minute pattern that whispers through clocks and cables. These findings are not widely shared. Within agencies responsible for critical infrastructure, they appear in internal reports as low-level periodicities of unknown origin recommended for observation, but not flagged as emergencies. The language is calm and technical. It notes correlations with magnetospheric oscillations already under study, suggests that coupling between the field and long conductors may be slightly stronger than previously modeled, and proposes minor adjustments to filtering algorithms. In the smaller circles of researchers who have followed 3I Atlas from the beginning, the convergence of these observations carries a quieter, more speculative meaning. The idea takes shape that the phenomenon has moved beyond the stage of affecting instruments directly looking at it, and now resides as a gentle modulation within the systems that form the nervous tissue of modern civilization. The same harmonic structure that once appeared as a line in a spectrum and as rings in a coronagraph image now seems to be present as a timing preference in clocks, as a recurring phase in cables, as a background beat in grids and positioning signals. The notion is not that the infrastructure has been overtaken or controlled. Nothing in the data suggests commands, messages, or directed interference. Instead, the systems appear to be sharing in a subtle resonance, as if their own sensitivities have allowed the planetary field, now carrying the persistent imprint of the event, to write a faint rhythm into their operation. Like long pendulums disturbed by a distant tremor, they swing by barely noticeable amounts, not enough to alter their purpose, but enough to show that they are part of a larger, slowly oscillating medium. Some frame this in terms of coupling and feedback. The world already sits within a web of relationships between solar activity, geomagnetic conditions, and technological systems. What 3I Atlas seems to have added is a new stable tone within that web, a narrow band of coherence that rides atop the usual noise. Once established, such a tone can persist, sustained by the energy of the broader environment, requiring no further input from its original source. This idea leads to long, quiet discussions about memory and physical systems. If fields can carry patterns long after the objects that shape them have faded from direct view, then the event associated with the visitor does not end when the last ring disappears from the coronagraph. It continues as a condition, a steady, nearly invisible modulation in the environment through which signals and currents flow. The name that some have begun to use for this state atlas condition reflects that shift. It no longer refers primarily to a moving body in space, but to a mode of behavior in the planetary field and its infrastructure. Outside these circles, daily life goes on unmarked. Lights turn on, messages cross oceans, satellites orbit. Few suspect that buried in the logs and traces of their systems, a distant encounter has left a soft repeating signature. For those who know where to look, however, the sense grows that the line between observer and observed has blurred. The networks built to watch the sky now carry within them a part of what they once watched, and the quiet unison of clocks and cables stands as a continuing reminder that the story of Three Eye Atlas has expanded from an object in the heavens to a frequency that gently and persistently lives inside the world's own technological heartbeat, beneath the restless air and the delicate sway of the magnetosphere. The solid parts of the planet seem at first to lie outside the reach of the Atlas condition. Rock, water, and deep interior structures appear indifferent to the gentle rhythm that touches clocks and cables. Yet as monitoring continues, attention turns toward instruments that listen not to fields or light, but to the slow motions of the Earth itself, and to the faint vibrations that travel through its interior and its oceans. Along tectonic boundaries and quiet continental interiors, seismographs record the constant tremor of the planet. Most of what they capture belongs to familiar categories: local quakes, distant earthquakes arriving as rounded waves, the low murmurs of ocean surf and atmospheric pressure. When analysts comb through long stretches of these records with the same care now given to magnetic traces, they begin to notice a minute repeating feature in the background noise. Every span of a little over 9 minutes, spectral power in certain low-frequency bands rises by a fraction, and then settles too gently to register as an event, yet too regular to dismiss as chance. To test whether this is an artifact of the instruments, they compare stations on different continents and on different kinds of crust. The pattern persists across many of them, though with varying strength. Seismographs nearer regions where the magnetic field is already known to ripple more strongly show a slightly clearer effect, as if the oscillation in the field is encouraging faint mechanical motions in the solid earth beneath. The amplitudes involved are extremely small, far below what any human could feel, but the statistical presence of the cycle is hard to ignore. Under the oceans, a different set of ears listens. Networks of hydrophones gather the low, long sounds that travel through deep water. Here too, when the data is examined with the known period of the Atlas condition in mind, slight periodic changes come into view. Acoustic background levels in specific narrow bands rise and fall with the same quiet regularity, as though the water column is responding in sympathy to a driver that does not originate in its own dynamics. Some of this response may be indirect. Variations in the magnetic field can alter the behavior of charged particles in the ionosphere, which can in turn change atmospheric currents, which then modulate pressure on the ocean surface. Through such chains, a faint pulse in fields can over time leave an imprint in waves and in the sea floor. Yet the neatness of the period and its alignment with the signatures seen in other domains suggests that more than diffuse coupling is at work. It is as if the planet has acquired a new shared mode of trembling, almost too soft to measure, but already part of its ongoing motion. Evidence from the deep interior adds another thread. Arrays that monitor minute variations in the length of day and in the wobble of the planet's rotation show a slight recurring pattern superimposed on their usual slow drifts. Tiny deviations in the spin rate, measured over many cycles, gather into a waveform that matches the now familiar interval. The changes are measured in parts per billion, invisible to ordinary life, yet they indicate that angular momentum is being redistributed in a rhythm that echoes the Atlas condition. Some theorists propose that the pattern arises from subtle exchanges between the fluid outer core, where the planetary dynamo generates the magnetic field, and the solid mantle above. In this view, the imposed rhythm in the field nudges flows in the molten metal, which then press back against the overlying rock in a repeating pattern. The effect is comparable to a very slow, very gentle tide within the deep interior, driven not by the gravity of a nearby moon, but by a structured memory embedded in the field itself. As these hints accumulate, they bring with them a shift in perspective. The atlas condition no longer appears confined to instruments or to the immediate environment of modern infrastructure. It shows itself as a property of the whole Earth system, present in fields, in water, in stone, and in the motion of the planet around its own axis. The event that began with an impossible color in the spectrum of a distant visitor now seems to persist as a barely audible tone in the body of the world. The language used to describe this remains cautious. Reports speak of weak, coherent modulations of global oscillations of correlations that merit further study. No one claims that 3I Atlas has altered the nature of the Earth in any dramatic sense. Mountains do not move to its rhythm. Oceans do not rise and fall by its command. Yet in the delicate domain where precision instruments listen, a new line has been added to the background score, one that was not there before the visitor came, and that does not fade when it leaves direct observation. In private, some researchers find the idea calming rather than alarming. The power of the effect is small, its reach more suggestive than practical. It implies that the planet is capable of incorporating even strange encounters into its ongoing patterns, absorbing an external rhythm and letting it join the countless cycles that already govern climate, weather, and geology. The atlas condition becomes, in this view, one more layer in the nested motions of a world that has always been in quiet conversation, with its sky now carrying within it the soft echo of something that once passed near the sun and then moved beyond sight, leaving its trace in the slow, shared tremor of stone and sea. As evidence of the atlas condition accumulates across fields, oceans, crust, and circuitry, the question of what to do with it shifts from scientists alone to institutions. The early phases of the event were marked by urgent messages, emergency calls, and dense technical exchanges as teams tried to keep pace with a rapidly unfolding anomaly. Now the behavior has settled into something steady, faint, and persistent. The urgency fades. In its place comes a different challenge: how to live with a phenomenon that does not end, yet does not demand immediate intervention. Space agencies and observational networks convene formal reviews. Committees gather in conference rooms under neutral lights with long tables and carefully prepared agendas. Presentations summarize months of work in measured tones. They show the evolution of 3I Atlas from a catalogued object into an emitter of impossible light, a source of synchronized timing, a driver of gentle non-gravitational drift, a transient ringed geometry at the heliospheric current sheet, and finally into something that can no longer be seen directly but remains audible as a pattern in the environment. The conclusions, when written, are cautious. They state that the original object is no longer detectable as a distinct source within current sensitivity limits. They note that a coherent modulation persists in the geomagnetic field and in certain technological systems, with a period matching that observed during the object's active phase. They recommend continued passive monitoring, refinement of models, and integration of the phenomenon into broader studies of solar-terrestrial coupling. The language is precise but subdued. It treats the atlas condition as a feature to be catalogued alongside other long-term variations, not as an emergency. Funding decisions follow the tone of these reports. Dedicated campaigns that consumed telescope time and specialized analysis are wound down. Proposals to build new instruments tailored specifically to the condition are redirected toward more general goals. The phenomenon is folded into existing programs that already monitor space weather, planetary dynamics, and global infrastructure stability. In this way, the atlas condition moves from the foreground of attention to the background of routine observation. Yet not everyone finds this transition entirely comfortable. Within small teams that spent long months tracing the rhythm through light field data and stone, there remains a sense that something significant has occurred, something that does not fit into the standard categories of storm cycle or slow drift. For them, the decision to treat the condition as simply another environmental modulation feels both practical and incomplete. It acknowledges what can be measured but leaves open what cannot yet be explained. Publicly, the story is even simpler. Early notices about an unusual interstellar visitor fade from news feeds. Later developments involving synchronization anomalies and faint rhythms in magnetometers never reach wide audiences at all. When journalists inquire, they receive careful statements about calibration issues, complex interactions between solar wind and field, and the need for further study. No falsehoods are told yet. The full arc of the phenomenon, from impossible line to persistent planetary resonance, is rarely presented in one piece. Over time, the absence of new dramatic events makes attention drift. Other topics rise to fill the spaces once briefly occupied by mentions of 3I Atlas. The object joins a long list of curiosities that stirred specialist interest and then slipped into the deeper layers of scientific literature, where only those already searching will find them. The Atlas condition continues, but it does so quietly in journals and internal reports, rather than in public imagination. Inside laboratories, the work takes on a different character. Rather than chasing a moving target, researchers begin to treat the persistent rhythm as a stable background against which other phenomena can be measured. In magnetospheric studies, it becomes a test signal that reveals how well models account for couplings between solar wind field and ionosphere. In infrastructure analysis, it serves as a benchmark for the sensitivity of grids and cables to external influences. In planetary physics, it is used as a probe of how deeply and in what manner rhythmic forcing can penetrate into oceans and crust. This repurposing does not erase the event's origin. Those who work closely with the data still remember that the signal was not always part of their world. They recall times before the forbidden line appeared, before clocks aligned too well, before storage systems began to share an unfamiliar pattern of errors. For them, the condition is both a tool and a story, a permanent addition to their measurements, and a reminder of a transient object that once transformed the sky into a coordinated experiment. Some reflect on the broader implications. The Atlas condition suggests that a system can move from object to environment, from something pointed at to something lived within. It shows that observation is not a one-way act by which instruments capture external behavior, but part of a larger interaction in which the act of looking can invite shared structure. Light from 3I Atlas entered telescopes, passed through electronics, and came to rest in storage arrays. Along the way, the same pattern that shaped the light appeared in timing and fields and in data until parts of the observing network themselves became carriers of the signature. This does not mean that the phenomenon is conscious or communicative in any familiar sense. The patterns it leaves are simple, repetitive, and limited to narrow bands. They do not encode messages in human language or direct complex outcomes. Yet they are also not random. They show a preference for coherence, a tendency to maintain harmonic relationships across different domains. In that preference, some see a hint of how complex systems might extend themselves not by building larger structures of matter, but by seeding stable patterns into existing fields and networks. For now, such ideas remain speculation held gently and without insistence. The measurable reality is that a faint regular modulation exists where none did before. It can be modeled, tracked, and perhaps in time fully explained in terms of physics that, while subtle, remains continuous with what is already known. The deeper questions about why this particular pattern arose, why it spread as it did, and whether it represents a rare coincidence or a common but rarely noticed mode of interaction are left open. On clear nights, telescopes still sweep the regions of space where Three-Eye Atlas once traveled. They find other objects, other visitors, each with its own path and character. None shows exactly the same combination of spectral thermal timing and orbital anomalies. The sky in that sense returns to its familiar diversity, yet the instruments that watch it are no longer quite as they were. In their shared timing and their subtle responses to the planetary field, and in the contents of their archives, they now carry a quiet record of an encounter that has become a condition, a background note in the ongoing music of Earth and its surroundings. In the months and then years after Three-Eye Atlas slips from direct view, the sky regains its ordinary calm. Nights pass as they always have, with constellations, rising and setting planets tracing their slow paths among the stars, and meteors briefly scratching bright lines across the darkness. The object that once occupied charts and schedules no longer appears in any finder scope. Ephemerides retire its line, moving it from active tables to historical records. To anyone who steps outside and simply looks up, nothing seems altered. The dome overhead is as quiet and as familiar as before. Yet for those who listen with instruments rather than eyes alone, the quiet sky now holds an extra layer of structure. Magnetometers still trace the slow breathing of the planetary field, and within that breathing the faint regular rhythm associated with the Atlas condition. Clocks still keep their careful time, and in the comparisons between them, the same gentle tendency toward shared oscillation persists. Communication cables and power grids still carry their ceaseless flows, and in the statistics of their fluctuations, the repeating signature remains. None of these effects rises to the level of a storm or a disturbance. They are instead part of the background, as soft and steady as the pale blue glow of daylight. Observatories continue their work much as before, scheduling nights for supernovae, exoplanet transits near Earth objects, and distant galaxies. Three-Eye Atlas appears now primarily in teaching examples and in specialized seminars, a case study in how a single event can link many domains of measurement. Students learn how an anomaly in a spectrum can lead to questions about timing, how timing can lead to field studies, how fields can lead to questions about infrastructure and planetary response. The story serves as a map of how modern observation works, not as separate efforts, but as a connected web in which light, data, and environment all participate. From time to time, someone suggests a new check. A group compares the current strength of the Atlas modulation to its strength a year earlier, looking for signs of decay or growth. Another team tests whether the rhythm remains aligned with the rotation of the Earth or with the changing angle of the planet to the Sun. The results are modest, yet intriguing. The amplitude drifts slightly, sometimes weaker, sometimes stronger, but never vanishing. The phase stays coherent enough that when aligned properly, cycles from distant years still overlay with a precision that hints at an ongoing self-sustaining process. Theoretical work continues in parallel, moving at a slower pace than the early rush of observation, but with a wider gaze. Some models treat the Atlas condition as an extended resonance, an example of how a narrow band of order can be introduced into a complex system and then maintained by the system's own energy. In these accounts, the heliospheric current sheet, the solar wind, the geomagnetic field, and the infrastructure of a technological civilization together form a medium capable of storing and circulating a pattern once it has been established. 3i Atlas becomes in such models less a unique object and more a catalyst, a circumstance that revealed what such a medium can do. Other models attempt to stay closer to the specific history of the event. They explore how a structured emitter passing through the inner system might tune itself to the natural frequencies of the solar environment, aligning its pulse to channels that carry it most efficiently. They examine how that pulse might couple to planetary fields, how those fields might then impress the rhythm onto systems that rest within them, and how those systems might, by their own responses, feed a small portion of energy back into the pattern, closing a loop. In this framing, the Atlas condition is a demonstration of mutual influence, a quiet, continuous exchange between object, star, planet, and machine. Where these lines of thought lead depends as much on philosophical preference as on equations. Some are content to see the event as a rare but natural occurrence, an accidental resonance between a passing body and a receptive environment. Others leave room for the possibility that 3i Atlas was not entirely the result of blind processes, that its precise spectral behavior, its measured adjustments in orbit, and its ability to move from matter into pattern reflect some level of design by entities long gone or far away. There is at present no decisive evidence to force a choice. The condition persists either way, indifferent to the stories told about it. In the end, what remains most tangible is not a conclusion about origin, but a change in how the sky and the planet beneath it are understood. The boundary between outside and inside, between cosmos and world, appears less absolute than before. A distant visitor once marked the sun's neighborhood with an impossible color and an unlikely synchronization. That mark has settled into the fabric of fields and systems that surround and inhabit the earth. Instruments that begin the night by turning their mirrors outward end it by recording a rhythm that now lives as much within their own operation as in any point on the star map. For those who find themselves awake in the small hours, watching status lights blink in control rooms or reading slow graphs on screens, there is a particular kind of reassurance in this state of affairs. The universe has shown that it can send a complex coordinated event through the solar system without violence, leaving behind not scars but a soft enduring trace. The quiet sky above and the faintly structured field below together offer a reminder that the stories written in starlight do not always end with impact or disappearance. Sometimes they end by becoming part of the background, woven delicately into the ongoing hum of a world that carries deep within its rhythms the memory of having been observed in return.